a really warm welcome to you all to our STEM Inspiration Week, which is hosted by STEMPOINT East. Lovely to see so many schools here today. And this morning we have got a fantastic talk from the National Museum of Computing, and I'd like to welcome Anne-Marie Langford in a moment. But before we do, please do make sure that your cameras are turned off and your microphones are muted, just so that we can minimise the background noise. Do keep monitoring the chat, please, teachers, and perhaps nominate somebody to be at the keyboard. There will be some questions, and perhaps you want to make some comments throughout the talk as well, and we will monitor that. And please don't forget that the session's being recorded, and we will send you a link to this at some point later on. So without further ado, let me introduce you to Anne-Marie Langford from the National Museum of Computing. Welcome, Anne-Marie.
Hello everyone, I'm really pleased to be joining you here at the National Museum of Computing. I am sitting in the museum, and we are about to look at how code breakers in Block H, which is where the museum is now, worked to decipher code from during the Second World War. But before we do that, it would be really great if I could get a sense of who's on the call. So if you could just put in chat who you are and how many there are of you, that would be really great. I've got lots of questions and answers. This is a really interactive session, so it's really important that your chat is on and working. Otherwise, it's just going to be me talking to myself, and that won't necessarily be useful or interesting for anyone. So, lovely. Hello to Ashcroft High School. Thank you for getting in touch. Is there anyone else? You must all be here. Lovely. Hello, Stambra. Lovely to hear from you. That's fantastic. Hello, Cardinal Newman. Lovely to see you. And we've got a fair few from Ashcroft, haven't we? That's great. And I'm teaching lots of different year groups, so that's great. And a Spanish group as well. Unfortunately, the session won't be in Spanish today. That could be a good thing, could be a bad thing, depending on your point of view. Hello, Rickmansworth School. Oh, hello, Claire. What school are you representing? And hello to the Home Education Group from Norfolk. It's great to have you joining us. We are actually planning some home education visits for the museum. We've got a remote visit planned for the 16th of November. So if you want to drop me a line, I will send you my email address so that you can get in touch and find out a bit more about that. Okay, so we've got Cardinal Newman, so have we got everyone here now? Before we get going then, I think you were asked in the chat to make sure that you either have your worksheets available to you or pen and paper. Everything is on the presentation. So if you haven't printed off the worksheet, you should still be able to get involved. We've set that up so that you can do that. So if we think we have everyone, I'll get started because we've got a nice meaty session to look forward to. Lots of information for the brain, if that makes sense. Okay, right, I'm just going to go ahead and share my screen and my PowerPoint. Okay, so this session has been called using maths to keep our secrets safe. We also call it deciphering the Lorenz machine, because we're going to be looking at how the Lorenz machine and how cryptographers use maths to keep things safe. But before we get going, I just want to ask everyone, what is cryptography? Can you put that in the chat for me? Can I just put, I need to share that so that I can see the chat. Okay, so hopefully you can all see that. Lovely, and I can see the chat. Brilliant. So, what is cryptography? Why do you use it? When do you use it? And how can you hide information? So, they're your 4 questions. I'm just going to give you a couple of minutes now. So pop your answers in the chat and I'll be looking at them to see how we're going. So what is cryptography? Somebody's answered encrypting and decrypting messages. That's brilliant. So hiding things. Why do you use it? To help secure data. That's exactly right. When do you use it? So when would you use cryptography? And how do we hide things using cryptography? Alex says all the time. That's right. We do use it all the time. And most of the time we use it without thinking about it. We're actually using it right now because on this Zoom call, this data is being encrypted to stop people from barging into our meeting and also listening into our meeting. So that's great. So that's right. Cryptography is the art of hiding information. So it involves codes. So whoever was saying coding, that's right, to convert information, and we use it to keep things secret. And we use it all the time without even thinking about it. If you WhatsApp, when you share things, it all gets hidden. So there are 2 main ways that you can encipher something. You can scramble it up, or you can combine it with other information, so you can add things to it. So here's an example of an enciphered secret message that was used by the Nazi High Command and was enciphered by a Lorenz machine. And as you can see, it's absolute gibberish. And we're going to find out how it becomes this absolute gibberish in the session. So, very quickly then, can you match these words with their definition? So what I'd like you to do is I'd like you to pair the words. So for example, encryption, 1. What definition does that belong to? Is it A, B, C, D, or E? And then you can put them in the chat. So you can put like 1D, 2C, whatever you think works. So just pop those in the chat. If you work, I'm going to give you a couple of minutes. And you can pair the word with the definition. Excellent. So we've got an answer already. Someone thinks that encryption is converting coded information into a readable format. Somebody else thinks that it is data and text that has been encrypted using an algorithm or cipher. Someone else thinks it's the process of converting information into a format that is unreadable to an unauthorized user or person. So somebody thinks that for decoding, decoding is converting coded information into a readable format. And we've got somebody here who says plain text is data that has been that is in a basic readable format. This is fantastic. We've got some great answers rolling in now. 5D, decoding. Maybe have a look at that answer there. Somebody thinks that encoding is G, converting information into a coded format. So we've got some great answers here. Why don't we look at them now? Here we go. So encryption is data or text that has been put into a the process of converting information into a format. Plain text is the data or text in a readable format. Cryptography is the practice or study of processing, writing or solving codes. Decoding that is where you convert the coded information back into a readable format. Ciphertext is the data text that has been encrypted. Encoding is converting that information to the coded format, and decryption is the reverse. So well done for getting involved everywhere. There were some great answers. So here's a word for you to decrypt. Now, before we get into this, the code breakers use information, they use clues all the time. So I'd like you to have a guess at what this word might be in its plain text format. So the clues are that this word is 8 characters long. So you're looking for a word that is 8 characters long. You're looking for a word that is related to computer science. So think of some of the words that you might use in computer science, and I guarantee you this is the word that is used the most. And it has been written using an additive cipher. So what we have done is we've added some gibberish to it, and you can see the key, or the gibberish that we have added to it, is A, B, C, D, E, F, G. So that probably won't help you too much, but the first 2 clues will. I'd like you to guess, just guess, a word that is 8 characters long and that relates to computer science, and put it in the chat, and let's see if we can figure out what the word is just by using our best intelligence guess. Okay, so someone from, hey, brilliant. A few schools are getting this right now in the chat. So 7E have guessed computer, and Cardinal Newman School have guessed computer, and Stanbrook School have also guessed computer, and you are in fact right. So that word is computer, and that's what cryptographers did. They used intelligent guesses to help them to hack ciphers. So you're already well on the way to being computer decoders, decryptors. So this word was enciphered using the Lorenz stream cipher system, and it's an additive cipher. So what you do is you find your letter. So let's say we've got the letter C, and we know that the key is A, B, C, D, E, F, G. So we've added the letter C to the letter A, and that gives us the letter F. So we've got a step through example here. You add the letter F to the letter A, and you've got the letter C. So, and vice versa, if you add the letter C to the letter A, you get the letter F. So if we step through how this works then, here are F to A is C, O to B is E, M to C is L, P to D is 8, U to E is, sorry, you get the idea, okay? So yeah, I plus E equals U, X plus F equals T for computer, and G plus 5 equals E, and B plus H equals R. But before these letters are they're actually sent as 5-bit binary code. So the letters from A to B are actually enciphered using these 5-bit binary codes, but they represent letters of the alphabet or numbers. So they're added together using a system called modulo 2. So we're going to talk a little bit about that. So how the Lorenz machine works is it takes its 2 characters, it takes its plain text character, and it takes its key character, and it creates a new set of characters. But it does this using the 5-bit binary code. So let's say we've got our plain text C and we add it to A. So the 5-bit binary code is there, that is added to that, and that gets that. So we get our input and our output, and that creates a new character. And then the process is reversed. Okay, So the way this works is, if you have a 1 and a 1, that makes a 0. If you have a 1 and a 0, that makes a 1. If you have a 0 and a 0, that makes a 0. If you have a 0 and a 1, that makes a 1. And if you have a 1 and a 0 and a 1, that makes a 1. And if you have a 0 and a 0, that should also make a 1. So that's how that works. But we're going to focus on the characters today. So we're going to have a go at this now. So I've put my addition square there, and that's for anyone that doesn't have their addition square worksheet with them. But we're going to have a go at trying that now. So you're going to try enciphering and deciphering your own activity. So if you've got your worksheet, you'll look at your worksheet for activity 2. If not, here are the instructions. You're going to choose one of the following 5-letter words. So you could choose your own, but for the sake of doing things quickly, because we've got a lot to get through, I've chosen 3 5-letter words for you: faith, happy, and shiny. So if you're just doing this on paper and paper, write yourself a little grid as shown on the screen. It says, so you write your plain text word out, then you create your key. Now your key could be anything. It could be first letters of your name, favourite football team, favourite band, whatever. Just choose something that's quick, that jumps into your mind. And if nothing jumps into your mind, just use the key A, B, C, D, E. The next thing you will do is you will add, using the tongue square, the addition square, your plain text word to your key to get your ciphertext. So if everyone is clear with that, I'm going to switch back to the addition square so that you can see the addition square very clearly. If anyone needs me to go through anything again, just put it in the chat. Otherwise, I'm going to flip back to the addition square so that you can encipher those letters. Now keep them private from the person sitting next to you, because the next step will be you swapping them over and trying to decipher. I'm just going to give you 3 minutes to do that. Let me know if you have any problems in the chat. We've just got 1 minute or so left now. Okay, so keeping your answer private now, we're going to look at a worked example. So you can see here. So let's say in our example, our plain text word is pizza, and we've added the key A, B, C, D, E. That's given us our ciphertext word Y8804. So what you can then do is you can take your key away from your ciphertext. So that's nice and simple. You take your ciphertext, you take your key, and you give the plain text word. So the next thing we're going to try is what you need to do is very quickly write down your ciphertext and your key and pass it to the person next to you, just swap. So do that really quickly, and then you're going to have 2 minutes to try and decipher their text. So I'm going to give you a couple of minutes to do that. Oh, I'm going to put the square back up to help you in case you haven't got the square. Okay, so you've had a couple of minutes to do that. How did you all find that? Did you all get the chance to encipher and decipher a very short message to your friends? Just send me a little a yes to say if you managed to do that, or no, that was tricky. Oh, I'm finding that tricky. Okay, so that it is quite an involved process. So even in its own way, it is quite tricky, but there's even more layers of kind of complication to it. So, however, okay, so the cryptographers here, they were able to intercept messages sent by the Lorenz machines. So the first message was intercepted in June 1941. However, it wasn't until August that we were able to begin deciphering. We used maths in order to do this, and this is really amazing. So if we go back to the square, what you'll notice is if you, there's like a relationship. So if we take the letter C and we've enciphered it to the letter A, there's a kind of mathematical relationship between these three characters. And what that means is you can add and take away those characters, and they refer to each other. So this enables us to reveal the original message using clues and using that process, reverse engineering that process. So if, as Peter was saying, you can reveal the original message by adding the key again, and that is kind of amazing. So here we go. So in August 1941, we were able to hack a Lorenz message. German operators sent 2 different Lorenz messages, but they used the same key. So we were able to get those messages and add the key to the other message and read the message. So we're going to have a go now at using this process. Now this process is really tricky, but I'm going to step you through it. So it looks really complicated, but a deep breath, we're going to put on our thinking brains and go through it. So if you imagine then, if you take your two messages, you've got two different messages with the same key. You then have two different plain text messages that existed somewhere over there, and we don't know what they are, but you have the same key. So if you've received two different plain text messages, let's call them C1 and C2, you can pair them together, and it can be expressed in this equation here. So you can take your two ciphertext messages and add them together, and you can get the plain text by taking away the key. So to try and decipher the message, we add the two ciphertexts together. This creates a random list of jumbled words, but we then use the key to get to the message. So when we add the ciphertext together, the key is removed from the message. That means the message has been decrypted, but the letters are still scrambled. And this is where our intelligent guess comes in. So if you've got a message and you think, well, hang on a minute, this is from the National Museum of Computing. So somewhere in that message, there has to be the word computer or computing. So if we unscramble, if we add the two ciphertext messages together and then we put the key on, no, the key is then removed. We then look for our intelligent guess, and that helps the message to become unscrambled. So, for those of you that have worksheets, in box 1, you need to add the words pizza and then the key. So in box 2, add the word 7 with the key A, B, C, D, E, 1. I think you might find this tricky if you found the first activity tricky. Right, sorry, no, this is an example. So in box 1, you would use the addition, you would add pizza to the key, and that would make your first ciphertext. I don't think you have to do this. I think this is on the worksheet. And then in box 2, you'd write 7 and you'd add that to the key. And then in box 3, what you would do is you would add the word pizza all enciphered to the word 7 that's all enciphered. And that would give you a mixed up word. And then you would decipher that. So the sum of C1 and C2 is added together. So this is what it should look like. No, it shouldn't, because that was happy and 8. Okay, so someone has done this with happy and 8. So just to confuse me a little bit. So you've got the word happy and you've added the key A, B, C, D, E, and that gives you the ciphertext Q, G, O, 8, H. You've then got the ciphertext, the plain text 8, and the ciphertext here. So what you do is you add this ciphertext to this ciphertext, and that gives you the words all kind of scrambled up. And then what you do is you have to unscramble them. Okay, so here it is with pizza and 7. So you've got pizza, which is enciphered to A, B, C, D, E, F, G, and that's Y8804. And then you have enciphered 7 to A, B, C, D, E, and you get IOT3F. You add the ciphertext for pizza to the ciphertext for 7, and you get this string of characters here. So you get W, U, K, T, K. So W, U, K, T, K, you take away pizza, and what happens? So, all right, sorry, a school has already started on that worksheet. So sorry to Canberra School. I'll just give you a minute to finish it off then. So with everyone else, although I've explained it. Do you want to have a go at that? So that's what's happening. So in box 1, we put the word pizza and we encode it with the key. And in box 2, and if you haven't got this, just write it out on the paper and put it in box C. I'm just going to give you 5 minutes to step through that by yourself. 5 minutes, 3. I'll give you 2-3 minutes to kind of go through it by yourself. And for those of you that haven't got the Tunny Edition square, I'll go to there. So I've just put a question in the chat. If we add pizza to A, B, C, D, E, what do you get? Excellent. So that is the correct answer. Now, if we add 7 to A, B, C, D, E, what do we get? So if we add 7 to A, B, C, D, E, what do we get? We've got lots of answers for pizza. That's magnificent. Great job, everyone. So the next thing is if we add 7 to A, B, C, D, E. So add 7 to A, B, C, D, E. What do we get? Excellent, excellent. The answers are all pouring in now. So it is that. So now the next thing we have to do is we have to add together Y8804 to IOT3F. What do we get when we add those two together? So you're going to get another random string of gibberish. Oh, fantastic. Well done. The schools have got very, very close to the answer there. Excellent, excellent, well done. Now what you'll find is if you take the characters, so some of the schools have got there, and the kind of, that bit is a W-U-K-T-K. So if you take W-U-K-T-K now, and if you take away the word pizza, for example, you should get the word 7 back. So, oops, try that. So if you take W-T-K, take pizza from that, it should reveal the word 7. Okay. Yeah. Sorry, I got a bit muddled in my brain. So what that means is you've got the two ciphertexts together and that reveals the key. So apologies, yes, you're right. You should get the answer A, B, C, D, E and not the answer 7. My apologies there. So just in the last 5 minutes, yes, Peter says, yes, you discovered the key. That's right, that's exactly right. And not as I had thought the word 7. Okay, so as you can imagine, this is a really complicated process and it takes a lot of hard work. So what we have done is we have put it into a computer program called Trinket. So some of you will have already been sent the link to a Trinket that does this. And so you'll be able to just play with this on your own as you wish. But for those of you that haven't got it, I'm going to call it up for you now and I'm going to demonstrate it. So I just need to stop sharing. Do I stop sharing? I have stopped sharing and I need to start sharing something else. Okay, so can you let me know, can you all see that Trinket on the screen okay? Excellent, right, so this is in Python code, the exact process that we've just done by hand, but doing it by hand is really slow and laborious. So we're just going to do it for real now. So the program's in this window here, and we can run the process in the other window there. So on this side of the screen, it explains what's going on. We can use our best guess. So let's say our best guess is secret. We can either change the guess or we can change the offset, so meaning the position at which we put it. So we're going to guess intelligently that somewhere in our secret message there is the word secret. But is it at position 1, position 2, position 3, position 4, position 5, 6, 7, 8, 9, 10? Can somebody give me a number and we will change the offset? Give me a number. Okay, 7. So we're going to change the offset to 7. and let's see what happens. So we've got some scrambled messages here, some scrambled letters, and this is the guess that it has given us. So it's just random gibberish, there's nothing there. So let's try a different offset position. We could try 5 or 6 or 7 or 8. Does someone want to give me a number and we will change the offset? Okay, we're going to try 5. Okay, so there we go. That is giving us some sort of gibberish as well. So I'm going to try 6 and see what happens. Right, if you have this, I suggest that you try it for yourself. Have a play and see if you can reveal the word. We're looking for the word secret message. So you want to find either part of that word or the word secret message. So have a little play and see if you can find it. I'll just give you a minute to do that, if you have it. If not, we can carry on guessing at possible offsets. So we could even try and change the guess. So would anyone like to give me another guess that we could look for in this trinket? What kind of words might be in a secret message? Oh, let's try the offset 8. Okay, and it's giving us GJS82QZ. I have a feeling that something strange is going on with our code. The code bit, can you make the code bit bigger? Does that help? Oh, do you want the code or do you want the... That is the code for the program. And that is the program being executed. So I'm not sure which bit you want making bigger. The bit where the program's being executed or the bit where the code we're talking about. Yeah, so that is what I can do. Okay. Right. We're running short on time now, so I have got time for some questions. And I'm going to get my colleague Peter, who's on the line. He's going to help me out as well with some of your answers. So does anyone have any questions? Can you put them in the chat?
I think they're really busy working out all the codes, Anne-Marie. I was trying to do that at home as well. Quite challenging. I've got one come up there. Can you see? When was the first computer made?
When was the first computer made? It was made, I mean, that's a really good question.
It's a tough one, isn't that?
You
need to define a computer first.
Yeah, you need to define a computer. So we say that Colossus was the first digital semi-electronic computer to be made. And that was made in 1942. 1943. But then other scientists say that ENIAC was the first computer ever made, and that was made in 1946.
But there was the Ishango bone, which was 20,000 years ago. And that was a computer.
Oh, can you tell us a bit more about that, Peter? What was that used for, do you think?
Well, opinions vary, but some people say it was basically an animal bone that had some lines carved on it. And it was found 20 or 30 years ago, I think, from memory. But it dates back that far. And some people think it was used to compute the way the tides work. So it's a computing device. It's not really a computer as we would know it. That's one option. Some people thought it was some sort of calendar. Mm-hmm. So that's another kind of computing device. Other people say all those grooves was so that it didn't slip out of your hand when you were holding it. So
That's the interesting thing about history, isn't it?
It
There's
is.
yeah, so
So
many different
somebody
variations.
asked which company made the first computers. So the first computer that was made to be used for business in the UK was the Leo, and that was used by Lyons Tea Houses. And that was in sort of the late 1940s, early 50s, wasn't it?
Not in 1951, they were using.
1951, that's right. I was going to say 1951.
Yeah. It wasn't the first commercial machine. The first machine you could go and buy if you were not military or government, so you were an ordinary business, the first machine you could buy, would you believe, was made in Manchester in 1951. It was actually made by the Ferranti company, who they used to make whacking great transformers for electrical supply, and they changed horses and started to make computers in 1951. Most people would think it would be an American company that you could buy a computer from, but in fact it was a Manchester company.
So we've got a question here. What kind of jobs can you get involved in computing? Well, that's a really good question, because there are loads of different jobs that involve computing. If you're good at maths and you love coding and logic, you can be a programmer. Now that's the obvious thing, but actually there are jobs in psychology that involve human computer interfaces. There is, sorry, someone's coming through. That needs to come, that person needs to be muted.
We will do that, Anne-Marie. I'll keep checking on that.
Thank you. So, yeah, so human computer interfaces. If you're creative, you can create, you can use computers to do artwork. You can, you know, you can do games design, virtual reality design, even interface design. So really, the possibilities are endless. You can almost match your skill set to whatever is going on in the computer industry. And what I suggest you could do is you could actually go out and have a look at some of the jobs that are out there and see, you know, where you could bring in your skills, because it's a growth area. So someone's asked, what is the most difficult job involving computer science? And I guess that depends on your point of view, because some people are, you know, really talented at maths, and they wouldn't find some of this math stuff quite that tricky. And they love problem solving. So I don't know, Peter, have you got a view on this? What do you think the most difficult job involving computer science is?
I think certainly the forefront of technology at the moment is looking at the evolution of artificial intelligence, which is in its sort of birth stages at the moment. It's pretty crude. Most of us know artificial intelligence as being Siri or Alexa or Hey Google. It's got a long way to go before it's really truly artificially intelligent.
I think cryptography as well, the field of cryptography is immensely complex. So things like cybersecurity and hacking.
Well, yeah, if you're looking for
hacking is very exciting, but also lots of problem solving.
Yeah, it's mostly, there are lots of jobs in cybersecurity. So that goes back to the earlier question. There's lots of opportunities in cybersecurity, and the cyber EPQ is a good start point for sort of.
Somebody asked the question, was it mostly women doing the decoding during World War II? And yeah, I mean, the answer is yes. There were thousands of women working on site at Bletchley Park, and they did most of the decryption work. It was all parceled up like a factory. So basically, you know, you did a little bit of the process. And very few people had oversight of the entire process, but they recruited bright young women that were good at puzzle, you know, doing crossword puzzles, jigsaws, maths, all sorts of things. There were literally thousands of women working here. So yeah, coding is, over time, has become something that is a male-dominated profession, but actually in the beginnings of computing, it was women that did the software engineering. But for some reason, that's all changed. So somebody said, who came up with coding? Well, actually, a woman called Ada Lovelace wrote what we recognise now as the first computer algorithm. She did that, I think, in 1864. So yeah, she was the first person to create a set of instructions for a computer.
And it was actually Ada Lovelace Day this week, so I think
Yes, it
teachers use
was.
that.
Yeah,
I'm
on
sure
the
you've done some work
13th.
around that this week.
So what was the first computer operating system? Peter, do you have any idea on this one? The first computer, was it a Linux or it was something?
No, Linux is very recent. It's difficult. These things emerged to make. Let's put it back into the 1960s for a moment. Most computers in the 1960s had no operating system at all. When you turned them on, it was like having a giant paperweight. It didn't do anything for you. All it did was consume electricity. So you kind of had to program it to do what you wanted it to do, and it would only do those things every time you switched the thing on. Now that meant you could probably load something pre-prepared into its memory, but there was no operating system that you interacted with as such on those early machines. You start to, in the sort of late 1970s, sorry, in the 1970s into the 1980s, operating systems started to evolve. But it's really hard to say who was first past the post on that, because there were people that realised that these things need to be made easier to use. Therefore, the thing needs to be able to start up on its own and get itself into a position where it's actually useful, without you having to spend maybe half an hour just messing around with the thing before you can actually do something useful to it. So, I mean, there's a bit of I've hedged the answer a bit there, but again, these things kind of emerge by a process of evolution. The first computer, that's a tricky one. Again, you need to define what a computer is.
I covered that by saying Ferenti. But I mean, actually, the American military built ENIAC before that. So it wasn't actually a company that built it. It was actually the military. The military were really interested in the possibilities of having computers automate processes like decryption to make things more simple. Somebody's asked what my job is. Exactly.
The first digital computer was built by it was built in 1940 by an American called Atanasoff. It was called the ABC, but it was immensely unreliable. But it was a digital computer, and so it predates Colossus actually. But the thing about it was only small. It could only do very basic addition, and it was incredibly unreliable. So it wasn't practical.
Okay. So one more question and then we'll finish, and then there's some information I'd like to share with everyone. So as soon as the screen shares back on, we can do that. So while I'm talking, basically, someone said, do you think there will come a time when computers take over all jobs? And I have to say, I think the answer is no, because I still can't share my screen. I think the answer is no, because there are certain things that are really difficult for computers to do. There are certain things that require human touch, and also in terms of economics, you know, it doesn't make sense for computers to be doing. There are physical things, you know, like picking potatoes in a field. Yes, you can get a robot to do them. Is it economically viable for a robot to do these things? Do we want robots to care for the elderly? I mean, yes, you probably could build a robot that could do that. It depends. I mean, I think there are certain things that humans can just do better. So please, can I share this information now? I still can't share my screen. So somebody said, how do you decide? How do you decide? Why is coding such a thrill? I think it's because it's problem solving, and when you solve a problem, it just feels amazing, doesn't it? We have the reward center in our brain that just gives us a little well done you when you solve a problem. Okay, so we have to go very, very soon. We might have overrun slightly actually, but I just wanted to let the teachers know that our partners, CoSpaces, we have created a recreation of Block H, which is where the museum is, and you can go into that space and you can play. You can play with Colossus machines, you can play with the Wrens, you can play with the engineers and the military police, put them in. You can add new things and you can code that space and do all sorts of exciting things with it. So if you just want to, I don't know, quickly get your cameras out or make a note of this, If you go onto that website, there is a free trial code, which is COS NMC. And if you go to that website and sign up, you get 30 days. You get space for 100 students to have a go in that environment. So you can just go and have a play and try it out for yourself, and let your students have fun with it as well. It might be good for the end of term or something like that. And then the other thing that we just want to tell you is that we are open for visits. So if you're able to get out, do come and see us. It'd be wonderful to have you here. But if you can't get out, we have just launched our remote learning offer, and you can access us via our remote learning portal. We've got tours and we've got workshops like this one that you can access. So do visit our website to find out more. Thank you so much for joining us at the National Museum of Computing, and thank you for getting involved. It was a very meaty session, and if anyone has any questions at all, or you want me to send through the trinket again, please drop me a line. I think STEMPOINT will be sending out details of the session.
Thank you so much, Anne-Marie, and to you as well, Peter. A really interesting session as well. Vanessa will be sending an evaluation teachers. If you could do that for us, that would be really, really useful. I think you definitely got our brains working, and it's just lovely to see modern application of what actually happened at Bletchley Park, which is such an amazing place in British history. So thank you very much. We learned lots today, and thank you to you. We look forward to working with you again. Thank you, everybody, and have a lovely weekend.